our work, Ladon, a high-performance multi-BFT consensus via dynamic global ordering. This is a joint work with my collaborators from the University of British Columbia and the Southern University of Science and Technology. Distributed systems often require multiple replicas to reach agreement on a shared state. However, in real-world scenarios, some replicas may crash down or act maliciously. To ensure consistency in such environments, we rely on Byzantine fault-tolerant consensus protocols, which allows a decentralized system to reach agreement among replicas despite Byzantine failures. A typical BFT consensus protocol is the practical Byzantine fault-tolerant. It follows a leader-based approach where a designated leader is responsible for broadcasting a batch of client transactions and coordinating with replicas to reach a consensus on its proposals. We observe that the transaction batch is significantly larger than the protocol messages themselves. So we can use this formula to roughly estimate the upper bound of the system's throughput. We can see that the leader's bandwidth limits the overall system performance of the BFT protocol. Many BFT protocols remain adopt the leader-based scheme, so they may suffer from the leader bottleneck. To mitigate the leader bottleneck, multi-BFT consensus introduced a parallelized approach. Instead of a single leader, multiple consensus instances run concurrently. Each replica acts as a leader for one instance and a backup for others. Each instance independently outputs a sequence of committed blocks. Then, these blocks are ordered in a global sequence and become globally confirmed. This makes the multi-BFT consensus functioning as a single instance system. Existing works adopt a predetermined global ordering. Each instance is pre-assigned some sequence numbers before block generation. For example, in this figure, in instance 0, blocks are labeled as 0, 3, 6, 9. These sequence numbers decide the final global position of the blocks. While this approach runs well in a balanced network, it introduces new challenges in the presence of stragglers. Stragglers are slow replicas which may be significantly slower than others due to limited computational resources, limited network bandwidth, or malicious behaviors, where replicas intentionally delay their behaviors. Predetermined global ordering makes multi-BFT consensus highly vulnerable to stragglers. For example, in this figure, we can see that instance 1 has a straggling leader that only outputs one block with a global index of 1. This causes 3 holes in the global log at position 4, 7, and 10, and prevents 4 blocks from being globally confirmed. It's the block 5, 6, 8, and 9. This reduces the system's throughput and increases latency. We run a state-of-the-art multi-BFT protocol with 16 replicas, among which there are 0, 1, and 3 stragglers respectively. We tested the performance under different workloads. We can see in the figure that with stragglers, the maximum throughput is reduced by about 90% of that without stragglers. Also, the latency increases more than 10 times of that without stragglers. Let's review the limitation of predetermined global ordering. A slow instance prevents other instances from confirming their blocks because a newly generated block can only allow each other instance to confirm one new block, like this figure shows. So we have a key observation that if a new block could jump directly to the front, it would no longer obstruct the global ordering. As shown in this figure, if the new block in the blue instance jump to the front, it will make the previous blocks confirmed quickly. To achieve this, we use a dynamically generated parameter we call rank to mark the position of a new block. The rank of a new block is the highest rank plus 1. For example, in this figure, now the highest rank is the maximum among 0, 3, and 3. So it's 3. So when we generate a new block, we will put it in the position of rank 4. Then blocks are first ordered by ranks and then by instance index. From the case, we can see that dynamical global ordering can mitigate the impact of stragglers. Now that we have discovered that using the rank parameter for dynamic ordering can reduce the impact of stragglers, we face a major challenge that how to generate a consistent and protocol compliant rank in a distributed system with Byzantine replicas. This major challenge can be divided into two specific challenges. The first one is different replicas may have different views on system state. For example, we can see in the figure that if replica 0 now see 4 blocks in the red and the green instances respectively, it will put the second block of the blue instance in the position of rank 4. And then it will global order the blocks like this. However, another replica 1 may, at the current time, it may only see 3 blocks in the red and green instances. So it will put the new block in the position of rank 3. And it will global ordering the blocks like this. We can see it's two different global ordering of blocks. This will violate the safety of the consensus. So everyone must reach consensus on the rank of a block. However, introducing an additional round of consensus for this would be unwise, as it would result in extra latency for each block. So we want to pitch back this the consensus on the rank on the consensus of the block. Specifically, we make rank as a parameter of the block when the leader proposes. When replicas reach consensus on a block, they also reach consensus on its rank. This way, they can locally use the rank for ordering without the need for additional communication. The second challenge is that malicious leaders can generate fake ranks, like in assigning a small or big value to the new block, rank value to the new block. To prevent this, the leader must find a way to provide evidence proving that it generates the rank follow the rule, and this evidence should be verifiable by other replicas. We require each leader to collect rank information from at least 2 F+1 replicas. It then increments the highest rank among these by 1 and assigns this as the rank of its proposed block. Each collected rank is sourced from blocks that have received sufficient votes and are accompanied by cryptographic certificates, which validate their authenticity. These collected ranks and certificates are then integrated into the proposal block for validation. Consequently, the Byzantine leader has very limited room to manipulate the rank. This figure shows the architecture of Ladon, consisting of 4 core components: rotating buckets, epoch pacemaker, consensus instances, and global ordering. Client transactions are equaled into rotating buckets and then consumed by concurrent BFT protocol instances. Each instance packs transactions into blocks, which are eventually globally ordered. Instances executed in epochs. We deploy all the protocols on AWS machines with 1 machine per replica. We deploy the experiment both in local area network and the wide area network. Our baseline protocols mainly contains 4 protocols. The ISS, Multi-BFT, and RCC are 3 predetermined global ordering protocols, and the DQ-BFT is another dynamic global ordering protocols. Our experiment aims to answer the following research questions. The first one is, how does Ladon perform with varying number of replicas as compared to the baseline protocols? The second one is, how does Ladon perform under crash and Byzantine force? This is the throughput and latency of Ladon and other protocols with varying number of replicas in wide area network environment. We can see from figure A and figure C that without stragglers, Ladon shows comparable throughput and latency with the predetermined protocols. From figure B and D, we can see that with 1 straggler, Ladon shows superior throughput and much lower latency than the predetermined protocols. If we compare the figure A and B, we can see that throughput of predetermined global ordering protocols significantly drops in the presence of a single straggler. In contrast, dynamic global ordering protocols are less affected by the stragglers. This is a similar set of the experiment in the local area network. All the protocols exhibit similar performance trends to those observed in the wide area network environment. We study how crash force affects the throughput of Ladon. This figure shows the throughput average over time. A crash occurs at 11 seconds, causing the throughput drop to 0. Because the wheel change timeout is set at 10 seconds, so the wheel change process is completed at about 21 seconds, at which point the throughput begins to recover. A new epoch starts at the 26 seconds, and each subsequent short drop to 0 is corresponding to an epoch change. This results in this is the impact of Byzantine leaders on Ladon. The 2 figures show that the impact of Byzantine stragglers on the system's performance is only slightly more pronounced than that of honest stragglers. This is because the manipulation of ranks by Byzantine stragglers is limited by our protocol design. In summary, Ladon is a high-performance multi-BFT protocol that mitigates the impact of stragglers. It adopts dynamic global ordering to assign a global ordering index to blocks according to the real-time states of all instances. It also uses monotonic ranks and pipeline their distribution and collection with the consensus process. That's all. Thanks for your attention.